It begins in contradiction. Ice that burns, a chunk of what looks like compacted snow, pulled from the seafloor or the frozen soil of the far north, and when touched by a flame, it does not melt, but flickers to life with a cold blue fire. It smolders gently in your hand like a magician's trick, whispering of chemistry that seems too strange to be real. Hello there, and welcome to the Sleepish Science. Whether you're tuning in tonight or this afternoon, or halfway through an indeterminable plane ride across time zones, I'm glad you're here. If you feel like sharing, I'd love to know where you're listening from and what time it is for you right now. And just between us, it's okay if you still think methane clathrate sounds like either a Hogwarts subject or something one might order in a particularly avant-garde cafe. So before you drift into dreamland, go ahead and like and subscribe. Your future sleepy self will thank you. Or at least give you a thumbs up in your dreams. Now back to the flickering flame. That combustible frost has a name, methane hydrate, or more precisely, methane trapped within a hydrate lattice of water molecules. Not exactly a cozy bedtime phrase, I'll admit, but the structure itself is delicate and remarkable. Imagine a snowflake that's learned the art of chemistry, crystalline cages of water that enfold a single molecule of methane, forming a solid white compound that is neither truly dry nor wet. The hydrate forms under just the right cocktail of pressure and cold, deep beneath oceans or within permafrost, where temperatures hover below freezing, and the weight of sediment or sea exerts constant downward force. And when it is released from those constraints, like an introvert abruptly invited to karaoke, the methane breaks free. That's where the fire comes in. I first read about methane hydrates in a quiet corner of a university library, where the silence was occasionally broken by the sound of someone falling asleep into their own textbook. What caught my attention wasn't just the chemistry, but the theatrical contradiction of it, that frozen ice could contain fire. A 1982 expedition by the Deep Sea Drilling Project first recovered methane hydrate samples off the coast of Guatemala, reporting white, waxy lumps pulled from sediment cores more than half a kilometer below the ocean floor. They fizzed audibly when brought to the surface, releasing trapped methane like tiny effervescent fountains. Researchers like Carolyn Ruppel, a geophysicist with the United States Geological Survey, have spent years unraveling where these hydrates form and how stable, or unstable, they really are. Her work emphasizes that methane hydrates are found primarily along continental margins, those submerged slopes between the edge of land and the deep ocean basin, where pressure and temperature work in concert to maintain the delicate balance of this fire ice. The methane itself is ancient, formed from the slow decomposition of organic matter buried in sediments over millennia. And when we say organic matter, we mean the remnants of long-dead plankton, algae, and seafloor microbes that, given enough time and insulation, release methane as part of their natural afterlife. It's worth pausing here, not for sentiment, but for perspective. The total quantity of methane locked in hydrate form around our planet is immense. Some estimates suggest more carbon is sequestered in hydrates than in all known fossil fuel reserves combined. But let's not reach for the dramatic just yet. It's not a ticking time bomb under the couch cushions of the earth. It is more like a sleeping dragon with a very particular bedtime routine. It prefers quiet, cold, and consistent pressure. And yet, the existence of this icy fire makes for an extraordinary scientific riddle. How does nature manage to sculpt such precise molecular cages? Why are they stable in some places and teetering in others? And could we, mere mortals with oil rigs and lab coats, ever hope to harness it, or should we simply tiptoe around it with deep reverence? As I once told a group of bleary-eyed undergraduates during a midnight field lecture, never trust a crystal that burns. It's either full of secrets or someone else's science experiment. Still, you can't help but marvel. Deep under Arctic tundra, or along the sinuous trenches of the ocean floor, these icy formations continue to sit, quietly holding their breath, and breath, after all, is where our story next flows. The thing about breath, especially ancient breath, is that it leaves traces, if you know where to look, beneath the rolling tundra of the far north, and deep under layers of ocean sediment. Methane hydrates slumber in slow geological time. They do not appear suddenly, nor do they leave without consequence. Their formation is the culmination of patience, of decaying organic matter, tucked beneath soil or seafloor, slowly compacted, fermented, and finally embraced by ice. These hydrates form where conditions are just so cold enough, pressurized enough, undisturbed long enough, like soufflés. They collapse easily if the conditions shift even slightly. In Arctic permafrost, those thick slabs of frozen ground that never fully thaw, even in summer, hydrate deposits lie locked beneath layers of silt and ice. When the permafrost is stable, the methane stays imprisoned within its crystalline cage, but when surface temperatures rise, and thawing begins to descend layer by layer, that hold begins to falter. The same is true beneath the ocean, though here it's less a matter of warming air than of a changing ocean blanket. At depths of around 300 to 1,000 meters, particularly along the outer edges of continental shelves, methane hydrates lie hidden in the sediment, stable only under a very particular mix of pressure and cold. This narrow band is known by geoscientists as the gas hydrate stability zone, a sort of invisible Goldilocks belt along the Earth's submerged margins. In the northern Pacific, off the coast of British Columbia, surveys by geologists like Kate Moran have mapped hydrate formations stretching for kilometers, buried under marine clay, held in place by a thick quilt of sediment. The methane here likely formed tens or even hundreds of thousands of years ago, as microscopic marine life sank and decomposed in oxygen-starved mud. Imagine for a moment a slow-motion graveyard where plankton fall like snowflakes, and every fallen creature becomes a whisper in the geological archive. These whispers compact, ferment, and finally release methane, which rises until it meets colder, higher pressure layers. There the water and methane engage in molecular origami, folding themselves into the remarkable ice lattice structure of hydrate. Of course, methane does not march upward in orderly columns. It seeps, it drifts, it swirls like fog through porous rock and sediment. Geologists have even observed hydrate deposits forming in surprising vertical bands, a kind of icy wallpaper climbing up through mudstone and sand layers. But not all hydrate is created equal. Some deposits are massive and well-structured, with visible chunks of hydrate mixed into sandy beds. Others form thin layers, more like icy frosting in geological pastry. The composition matters deeply, not just for understanding stability, but for anyone considering extraction, and that is where things get tricky. Because once hydrates begin to destabilize, through warming pressure changes, or even the gentle tremble of tectonic movement, the methane can be released suddenly, not just a whisper, but a gasp. That gasp, once heard, changes everything. It's what turns a frozen permafrost field into a pockmarked landscape of sinkholes. It's what transforms a quiet patch of ocean floor into a methane plume hundreds of meters tall, and it's what has climate scientists watching the Arctic with increasing urgency. In the Siberian tundra, researchers like Natalia Shakova and Igor Semiletov have documented methane bubbling from undersea permafrost on the East Siberian Arctic shelf. These are areas where hydrate deposits, once securely frozen, are now being exposed to warmer currents and thinning sea ice. The result? Fountains of methane rising from the seafloor, silent but potent. Methane, you see, is a powerful greenhouse gas. Molecule for molecule, it traps more heat in the atmosphere than carbon dioxide. That doesn't mean it lingers as long. Methane breaks down over a decade or so, but while it's present, it packs a punch. One might say it's the espresso of the greenhouse family, potent, fast-acting, and best handled with care. Of course, not every molecule of methane from hydrate ever makes it to the surface. The Earth is full of guardians, microbial, chemical, and geological, that consume, filter, or trap much of the gas before it can escape. But when hydrate deposits destabilize quickly, those defenses can be overwhelmed. Even in the absence of dramatic release, the mere presence of hydrates creates unusual landscapes. In the Beaufort Sea, for instance, bathymetric surveys have revealed strange mounds and craters, features called pingo-like features, and collapsed thermokarst formed as methane hydrates push up from below or dissolve, leaving behind voids and sinkholes. I once saw one described as looking like a pot of boiling oatmeal, frozen mid-simmer, which, depending on how poetic you're feeling, is either mildly delicious or deeply unnerving. So we have these vast frozen reservoirs, tucked under permafrost or seabed, containing gas that can both warm the planet and potentially fuel it. And we have a planet that is shifting slowly in some places, rapidly in others, altering the conditions that have kept these hydrates stable for ages. There is both awe and unease in that. To stand atop tundra that conceals prehistoric breath, or to float above an oceanic margin that conceals a chemical lattice of fire, is to feel history pressing up from below, and sometimes that pressure finds its outlet, not through a bubble, but through a tremor in the earth. Sometimes the earth sighs in silence, other times it rumbles with intent. Along the wrinkled edges of continents, where tectonic plates press and slide like slow-motion tectonic tango partners, methane hydrates lie in precarious balance. These oceanic margins, places like the Cascadia subduction zone off the Pacific Northwest or the Nankai Trough near Japan, aren't just geological boundaries, they're arenas of invisible tension, where hydrate deposits perch like frost on a trembling branch. You see, these regions are not stable archives. They shift, subduction zones, the places where one tectonic plate dives beneath another, generate some of the most powerful earthquakes on Earth. And it's precisely along these sloping undersea corridors that vast amounts of methane hydrate are buried, tucked within layers of sediment above fault lines and fracture zones. Here's where things get lively, in the deep sea kind of way. As tectonic forces rearrange the seafloor, nudging sediments, flexing faults, or even triggering undersea landslides, they can also disturb the temperature and pressure conditions that hold methane hydrates in their icy lattice. The hydrate doesn't take kindly to disruption. In a 2006 study led by Marta Torres at Oregon State University, researchers examined hydrate-bearing sediments near active fault zones and discovered that seismic activity, not necessarily dramatic but subtle and persistent, was linked to higher rates of methane migration. Like soda fizzing more vigorously after a jostle, the gas would begin to seep, bubble, and sometimes escape entirely from the disturbed sediments. And it's not just the shaking. Landslides, particularly submarine ones, can set off chain reactions that both expose hydrates and destabilize layers that had, until recently, been content to sit quietly in their muddy cloaks. One infamous example lies along the Storge Slide off the coast of Norway. Roughly 8,000 years ago, an underwater landslide there displaced thousands of cubic kilometers of sediment, creating a tsunami that reached far into northern Europe's coastlines. While not caused by hydrate destabilization per se, some scientists, including James Kennett of the University of California, Santa Barbara, have speculated that methane hydrate dissociation may have played a role in triggering or amplifying the slope's instability. The suggestion is that melting hydrates, by reducing the cohesion of sediments and releasing free gas, could weaken a slope just enough to tip it into collapse. And once a landslide begins, it can trigger additional hydrate dissociation by releasing pressure and warming buried sediments, unleashing yet more methane. It becomes, in short, a loop, a downward spiral, both literally and metaphorically. Of course, these events are rare, and the Earth is vast, but in a warming world, the risks may grow. As sea temperatures creep higher, not by much but enough, the upper boundary of the gas hydrate stability zone begins to retreat deeper. This can lead to the formation of what's known as a hydrate edge, where dissociation begins, and the sediments above become mechanically weaker. Geophysicists like Matthew Hornback have documented this phenomenon off the eastern coast of North America, where warming bottom waters appear to be migrating downward, nibbling away at the edges of the stability zone. In some places, hydrate dissociation is already underway, with methane seeps appearing where there were none just decades ago. It's not all doom and gas plumes though. In some areas, geological layering and sediment type offer natural protections. Thick impermeable layers can trap methane, much like a lid on a simmering pot, and microbial communities, as we'll explore soon, work tirelessly to oxidize and convert methane before it ever reaches the water column. Still, it's the combination of tectonics and hydrates that gives scientists pause. Unlike climate warming, which tends to unfold across decades, seismic events occur suddenly. If an earthquake were to rupture hydrate-rich sediments, especially those already teetering due to temperature changes, the release of gas could be swift and significant. And then there's the mystery. Because for every mapped hydrate deposit, there are likely many more we haven't yet discovered. The ocean floor is only partly charted. We are still learning the language of the deep. During a remotely operated vehicle dive along the Sumatran margin, a team from the Schmidt Ocean Institute unexpectedly encountered shimmering bubbles rising from what appeared to be a fault scarp, evidence of recent disturbance and active methane seepage. The site hadn't been catalogued. No hydrate deposits had been previously predicted there. The Earth had revealed a secret, as it so often does, just long enough for a robot to notice. I sometimes imagine the hydrate fields as old libraries with sleeping cats, mostly quiet, faintly mysterious, but prone to sudden motion when you least expect it. And in the folds of those muddy libraries, methane waits, occasionally nudged, occasionally shaken, occasionally awakened by the slow, ceaseless breath of the Earth itself. But even those breathless sighs leave behind stories, written in bubbles and buried deep in the ice. Each bubble tells a story. Trapped in ice, sealed in sediment, or exhaled softly from the seafloor, methane carries whispers of Earth's ancient breath, carbon once part of living bodies, now repurposed into a gaseous time capsule. To understand where we might be going, scientists often begin by listening to these tiny icy voices from the past. They drill down into permafrost and ocean beds. They slice through ancient ice. And from these chilled archives they extract clues, evidence that our world has released vast plumes of methane before, and the results were anything but quiet. In the ice cores of Greenland and Antarctica, atmospheric records stretch back hundreds of thousands of years. Bubbles trapped in the ice, microscopic and unassuming, contain ancient air. When researchers like Ed Brooke at Oregon State University studied these cores, they noticed something peculiar. In certain intervals, methane levels spiked sharply, often within just a few human lifetimes. These bursts seemed to coincide with abrupt warming periods, such as the end of the last glacial age. But warming, rapid even by today's impatient standards, didn't creep, it leapt. Within a few centuries, or perhaps even decades, temperatures climbed, sea ice retreated, glaciers withdrew, and in the wake of that transformation, the methane rose. But from where? One suspect: hydrate dissociation. Geological records suggest that massive methane releases, perhaps triggered by shifting ocean temperatures or sea level changes, may have emerged from destabilized hydrate fields. A warming ocean reaching just a few hundred meters deeper could have been enough to tilt the balance. Sediment cores taken from the Blake Ridge, off the southeastern United States, show a remarkable layering of organic material, hydrate-rich sediments, and telltale signs of past gas release. Pockmarked seafloor features called pockmarks, as charming as their name may sound, dot these regions created when gas erupts and leaves behind small craters, like exclamation points in the mud. Meanwhile, in deep marine sediments from the Santa Barbara Basin in California, a team led by Isabel Montañez from the University of California discovered distinct carbon isotope shifts, indicators of a past methane release event dating back over 55 million years during the Paleocene-Eocene thermal maximum. That ancient episode was marked by a dramatic global warming spike, a massive extinction of deep-sea life, and oceans turned slightly acidic, all possible echoes of methane suddenly rejoining the atmosphere. It's worth noting, for our comfort or curiosity, that not all scientists agree on the scale of methane's role in these warming episodes. Some argue that while hydrate release may have contributed, it was more of an accelerant than a cause. Others suggest that only a portion of the released methane reached the atmosphere at all, with much consumed by oceanic processes. But even if only a fraction makes it skyward, the implications remain sobering. Methane lingers in the atmosphere for about a decade, short-lived by greenhouse standards, but during that brief tenure, it captures heat with an intensity far beyond that of carbon dioxide. It is in effect the flashbulb of greenhouse gases, brief, bright, and potentially transformative. There's also a spatial fingerprint to consider. By mapping where gas seeps and hydrate destabilization zones appear, researchers can reconstruct ancient flow patterns and identify past regions of flux. One such map, produced by David Valentine and colleagues, shows a quilt of seep zones across the Gulf of Mexico, with some spots active today and others long dormant, suggesting that hydrate dissociation is not a new player in the Earth's climate theater, just a recurring one. And then there's the Arctic. The East Siberian Arctic shelf, perhaps the most hydrate-rich and vulnerable region on Earth, has offered its own share of warnings. Studies by Shekova and Semaletov have shown increasing methane concentrations above the water surface during recent years, sparking debates about whether a larger destabilization is already underway. Skeptics argue for seasonal variation, proponents warn of a tipping point already creaking underfoot. I once heard a paleoclimatologist compare ancient methane events to buried matches waiting for friction, not fires, necessarily, but ignitable. And when you walk across permafrost or sail above the ocean's edge today, the ground beneath still remembers where those matches were struck. Of course, history is not prophecy, but it is a whisper, an invitation to pay attention. In the soft clays of the seafloor and the deep-breathing ice of polar archives, we hear the echoes of warming past. They're muffled, yes, but urgent. Not because the Earth hasn't recovered before. It has. It always does. But because we, the current stewards of carbon and consequence, have never been here before, trying to read these icy scripts with hands that may be warmer than the page prefers. Still, even ancient breath is not just a warning, it's a thread. One that leads improbably to life. Where fire meets ice in the cold dark of the deep sea, something remarkable stirs, something alive. At first glance, a methane seep on the ocean floor seems lifeless. A pale mound perhaps. A slow trickle of bubbles rising from the sediment. Occasionally, a flicker of movement. A worm. A wisp of microbial slime. But then the camera zooms in, and suddenly you're looking at a metropolis. There are tube worms, long scarlet-plumed creatures anchored in white chitinous tubes, waving gently like a slow-motion kelp forest. There are squat lobsters, ghostly pale and watchful, darting between rocks. Mat-like communities of bacteria coat the seabed in pastel swirls of white, yellow and orange. In this twilight cityscape, the gas that elsewhere spells danger is here, a source of life. These organisms are not just surviving near methane, they are thriving because of it. Some of the earliest clues came from the deep Pacific, off the coast of California and Oregon, where scientists from the Monterey Bay Aquarium Research Institute, particularly Victoria Orphan and her team, used remotely operated vehicles to investigate strange shimmering landscapes. What they found was astonishing: entire ecosystems built around methane seeps, powered not by sunlight, but by chemistry. The key is something called chemosynthesis. While surface-dwelling plants and algae rely on sunlight to produce energy, these deep-sea organisms use methane. Or more precisely, they rely on microorganisms that metabolize methane, transforming it into energy in complete darkness, under immense pressure, and often at temperatures just above freezing. One of the stars of this invisible symbiosis is a partnership between two very small and very specialized creatures, anaerobic methane-oxidizing archaea and sulfate-reducing bacteria. The archaea consume methane and hand off byproducts to the bacteria, which in turn reduce sulfate. Together, they transform an otherwise uninhabitable niche into a thriving foundation for life. This relationship, discovered through techniques like fluorescence in situ hybridization and isotope tracing, is delicate and deeply cooperative, like a microscopic buddy cop duo, navigating the crime-ridden corridors of the undersea. Over time, these microbial mats accumulate, creating biofilms that offer food and shelter for larger creatures. Tube worms attach themselves to hydrate mounds. Clams and mussels settle in clusters. Even fish patrol the edges, eyeing the bounty. In a 2016 expedition led by the Schmidt Ocean Institute, researchers exploring the Gulf of Mexico's hydrate mounds stumbled upon vast fields of methane seep communities, some stretching dozens of meters. The sight was otherworldly: luminous white crusts of hydrate emerging from sediment, flanked by blooming mats of bacteria and bustling with life. It was, one scientist said, like finding a coral reef made of ice and breath. But perhaps the most surreal part: these ecosystems are not rare. They're just rarely seen. Along continental margins from Norway to New Zealand, from Chile to China, methane seeps have been quietly sustaining life for millions of years. Some communities are transient, flaring up and fading as methane flows shift. Others, like those along the Hydrate Ridge in the northeast Pacific, appear astonishingly stable, cycling methane and nurturing generations of tube worms over centuries. It's tempting to see them as exceptions, but they may be ancient archetypes. Before Earth had an oxygen-rich atmosphere, before green photosynthesis painted the planet's biosphere, methane metabolizing microbes may have been among the earliest forms of life. Some scientists believe these seeps echo conditions from billions of years ago, offering a glimpse into life's humble chemical beginnings. And they're not just important for biology, they're crucial to chemistry too. These microbial communities play a silent but vital role in regulating how much methane escapes into the ocean and ultimately the atmosphere. By oxidizing methane in situ, they act as biological buffers, trimming the peak of any potential greenhouse spike. It's not dramatic, but it's persistent. Like janitors working a night shift no one sees, they keep the system from tipping too far. That said, they have limits. If methane flow becomes too strong, say due to a landslide or rapid hydrate dissociation, these communities can be overwhelmed. Their metabolism slows, their buffering breaks down, and the gas escapes upward. Even so, their presence is a kind of reassurance that the Earth, for all its wildness, has built-in checks. And sometimes, those checks take the form of tiny creatures with no eyes, no lungs, and no awareness of their cosmic importance. I once watched footage of a tube worm slowly unfurling at a seep, its red plume gently pulsing in the current. The narrator, half scientist, half poet, simply said, "Here life borrows fire from the earth and gives back only silence." There's something humbling in that, because just above this vibrant darkness lies a world uncertain about methane's future. But here for now, it remains part of a slow, vital dance, a rhythm shaped by chemistry, choreographed by evolution, and performed in the shadows. And that rhythm may soon face a crescendo. You don't hear a crescendo in the deep sea. Not in the way orchestras suggest, anyway. There's no blaring brass or rising timpani roll, but if you listen in the right way with sensors, models, and a growing sense of planetary nervousness, you begin to sense the mounting pressure. Methane, for all its biological charm and crystalline elegance, has a fiery side. As a greenhouse gas, it's a heavyweight in a lightweight suit, colorless, odorless, and capable of trapping heat far more efficiently than carbon dioxide. And while it lingers in the atmosphere for a shorter time, its impact during that stay is disproportionately large, like a guest who crashes a party only briefly, but manages to reset the thermostat and break 3 lamps. So when scientists speak of hydrate destabilization, it's not just a geological curiosity, it's a climate wildcard, a potential tipping point. The idea is disarmingly simple. The ocean's warm, the warming seeps down, slowly but steadily, eroding the icy grip that keeps methane trapped within hydrate cages. As those hydrates decompose, methane escapes into the water column. Some is consumed by microbes, some dissolves, but some, particularly in shallow waters, reaches the atmosphere. If this happens slowly, the system might absorb the shock, but if it accelerates due to positive feedback loops or widespread destabilization, then the warming causes more methane to be released, which causes more warming, and so on. A loop, elegantly cruel. The Intergovernmental Panel on Climate Change, that careful choir of international consensus, has historically downplayed the likelihood of a catastrophic methane release. But recent research is nudging the tone. A 2020 study led by oceanographer Natalia Shakova found evidence that permafrost degradation on the East Siberian Arctic shelf could be releasing up to 7 million tons of methane per year. That's not apocalypse math, but it is more than most climate models had accounted for. Part of the problem lies in our models themselves. Many of them don't yet fully integrate methane feedbacks, especially from hydrates. These are hard systems to observe directly. They're buried, remote, and subject to wild variations in local geology, pressure, and microbial activity. It's like trying to predict a souffle's rise by poking the oven door and hoping for the best. Still, warning signs are growing. In the Barents Sea north of Scandinavia, long-term monitoring by Norwegian and German researchers has recorded thousands of methane seeps, many newly active over the past few decades. In areas once stable, methane now bubbles up in persistent trails, like breath rising from a planet slowly exhaling its ancient secrets. And in Alaska, thawing permafrost is producing thermokarst lakes, shallow dark pools that absorb sunlight, melt deeper ground and release methane in fizzing bursts. NASA's Carbon in Arctic Reservoirs Vulnerability Experiment project once sent airborne sensors across these regions and detected atmospheric methane concentrations well above expected baselines. These may be regional quirks, or they may be the tremors of a larger warming breath. It's important to note, with gentle emphasis, that a full-scale methane hydrate catastrophe, the so-called clathrate gun hypothesis, remains speculative. Most scientists agree it's unlikely in the near term, The world is warming quickly, yes, but hydrate systems are buffered by a host of physical and biological factors. We're not on the brink of planetary flatulence, but tipping points don't always arrive as singular events. Sometimes they creep. A few million tons here, a gradual thaw there, each addition tilting the balance, one carbon atom at a time. And the issue isn't just the methane itself, it's the role it plays in climate feedback. A 2022 study in Nature Communications modeled hydrate-related methane emissions under moderate warming scenarios and found that, even with modest releases, the additional warming effect could hinder carbon mitigation efforts, effectively locking in higher temperatures. Even with policy interventions, it's a reminder that Earth's systems are not linear, they are interwoven. A release in the Arctic can ripple into weather patterns in the tropics, affecting rainfall, agriculture, and ocean currents. What melts in the north can eventually move the winds in the south. I once heard a climatologist liken methane hydrates to the bass notes in a symphony, low, slow, and often overlooked, but capable of changing the entire mood when struck at the right or wrong moment. And that moment may be approaching, not as a sudden thunderclap, but as a slow rising hum in the deep. Even the smallest shifts matter. A fraction of a degree in water temperature, a slight change in ocean currents, a subtle acceleration in permafrost thaw. These don't make headlines, but taken together, they begin to sketch the outline of a warmer, wetter, and less predictable future. Still, in the quiet between data points, there is space for wonder. The methane itself is not malevolent. It is ancient breath, fossilized sunlight, a product of life, now looped back into the web it once helped build, and sometimes to study it, we have to follow the breath itself, down through the water, to the source, which is exactly what we've begun to do, with gentle glowing machines. They drift, rather than dive. Remotely operated vehicles glide through the dark like slow jellyfish made of wires and willpower. From the surface they are tethered by long cables, controlled by a team that includes marine engineers, geologists, biologists. More often than not, one deeply caffeinated person operating a joystick with monastic focus. When these vehicles descend, they leave behind light, time, and almost all signs of the familiar. What they find in return are landscapes shaped by gas and pressure, fields of methane hydrate that shimmer in artificial light, seeps that fizz like underwater champagne, and strange geological shapes carved by bubbles and buried flame. On a quiet day aboard a research vessel in the Gulf of Mexico, I once stood behind a pilot as we watched a remotely operated vehicle ease toward a seafloor mound. It looked at first like a pile of chalky rubble, then came the telltale glint, a crystalline cluster of methane hydrate protruding from the sediment, like a piece of ice that had learned to glow under scrutiny. We weren't the first to see it, of course. The vehicle had been here before, but the site had changed. The hydrate deposit was larger, its structure clearer. It had grown fed by steady seepage and perfect conditions, and around it, life moved. Clams gently fanning themselves, polyceti worms undulating like ribbons, and mats of bacteria expanding like living paint. These vehicles have become essential tools in the study of methane hydrates. They don't just observe, they collect. Robotic arms scoop sediment into sterilized tubes. Suction samplers draw in gas bubbles for analysis. Temperature probes are inserted into the seafloor to measure thermal gradients, and spectrometers detect chemical signatures invisible to the human eye. In one expedition aboard a research vessel operated by the Schmidt Ocean Institute, the team deployed a remotely operated vehicle to survey the Cascadia margin just off the Pacific Northwest. There, at a depth of nearly 1,000 meters, they discovered dozens of active methane seeps, each one bubbling methane directly from the seafloor. Some seeps were surrounded by vivid bacterial mats, others by bare sediment craters, all quietly exhaling into the dark ocean above. They even documented a hydrate structure nicknamed the White Fang, a slender towering spike of methane hydrate that had formed within a seafloor fracture. It looked like something you'd expect to find in a fantasy novel's frozen temple, not in a marine sediment basin. The footage was both eerie and beautiful, like peeking behind the curtain of a world still in rehearsal. Each seep, each hydrate mound revealed subtle evidence of dynamic change, shifts in sediment, layering, collapse pits, cracks in the seafloor crust, and sometimes the vehicles find more dramatic signs. In a dive off Svalbard in the Arctic, a remotely operated vehicle captured images of intense methane bubble plumes, columns stretching up several hundred meters through the water column. Some plumes were so vigorous they triggered turbulence, altering local currents. These weren't single bubbles drifting lazily upward, they were torrents gushing like underwater geysers. Such footage helps scientists refine their models, testing theories about gas migration pathways, hydrate stability zones, and the role of sediment porosity. They also offer glimpses of processes previously too deep, too subtle, or too sporadic to witness directly. One surprising discovery from these deep-sea missions is that hydrate presence can change quickly. In just a few years, sites can shift from dormant to active, from gas-rich to gas-quiet. It's a reminder that methane hydrate fields are not static archives. They're living systems, responsive, evolving, and often far more dynamic than expected. In a long-term study conducted by Japan's National Institute of Advanced Industrial Science and Technology, scientists used vehicle footage to document seasonal variations in methane flux at the Nankai Trough. They found that hydrate deposits and seeps responded not just to tectonic nudges, but also to changes in bottom water temperature, suggesting that even short-term climate variability could influence gas emissions. This discovery that hydrate systems might react on the scale of seasons, not just centuries, raised eyebrows and questions in equal measure. What else might we be missing? What other feedbacks, fast or slow, lie hidden beneath our ocean's heavy cloak? Still, for all their utility, remotely operated vehicles are not infallible. They cannot go everywhere. Deep trenches, steep escarpments, ice-covered seabeds, these remain for now, harder to reach, and their observations, while rich, offer only a snapshot. The seafloor, like any living system, changes continuously. But what these vehicles give us, besides stunning video and the occasional cameo by a curious octopus, is a lens into the life and motion of the deep. They let us watch hydrate deposits form and fade. They let us listen in a way to the Earth's exhalations, and they allow us to peer into places where fire, ice, and biology cohabitate in something resembling peace. On one dive, as a vehicle rose from a seafloor vent, the pilot turned to me and said, "It's like we're spying on a planet that hasn't finished being born." It struck me as oddly accurate. In these depths where methane hydrates flicker like dormant stars and bubble trails trace invisible maps, Earth still seems to be making itself, and perhaps, just perhaps, we're only beginning to learn its dialect. You might think of methane hydrate as the dragon in the basement, powerful, volatile, and best left undisturbed. But not everyone sees it that way. To some, methane hydrate is less a threat than an opportunity, a vast, untapped source of energy, lying just beneath the sea or frozen within permafrost. Not a monster, but a misunderstood mineral with a promising resume. The question is not whether we could use it. The question is whether we dare. Methane, after all, is the principal component of natural gas, and methane hydrate, sometimes called flammable ice in headlines with a flair for drama, contains enormous volumes of the stuff. 1 cubic meter of solid hydrate can release over 160 cubic meters of methane gas when warmed and depressurized. That's a lot of energy from what looks like frosted chalk. Given this, it's little wonder that energy researchers, especially in nations with limited conventional fossil fuel reserves, have turned their attention to hydrate fields. The deposits are vast, the potential is tantalizing, but accessing it, that's a different story. The basic problem is that methane hydrate is stable only under specific conditions. Cold temperatures and high pressure change either, and the hydrate begins to dissociate, releasing methane. That's excellent if you want the gas, but terrible if you don't want blowouts, landslides, or unintentional greenhouse releases. Early extraction concepts looked a bit like submarine mining. Drill into the hydrate-bearing sediment, depressurize the surrounding area, and collect the gas as it bubbles out. In theory, it's no more complicated than boiling pasta. In practice, it's more like boiling pasta on a mountain ledge, blindfolded, in a snowstorm, with your stove teetering over a landslide zone. Nonetheless, researchers pressed on. In Canada's Mackenzie Delta, more than a decade ago, scientists from the Geological Survey of Canada and the Japan Oil, Gas and Metals National Corporation conducted a field test. They drilled into permafrost and successfully extracted methane from hydrate deposits using depressurization alone. It was modest but promising, a proof of concept that whispered possible. Around the same time, in the Nankai Trough off Japan's coast, engineers began testing seafloor production systems. Their technique was similar: reduce pressure in a hydrate-bearing layer beneath the seafloor and collect the gas as it escapes. In 2013, they succeeded in producing methane continuously for 6 days. A few years later, with a revised setup, they managed it again, this time for over a week. Not exactly an energy revolution, but a beginning. Still, the challenges were immediate and sobering. The seafloor is an unpredictable place. Sediments can collapse, equipment must survive pressure, corrosion, and the occasional wayward octopus. And hydrate reservoirs themselves are not uniform. They vary in saturation, composition, and behavior. Some hold tightly to their methane, others release it explosively. Engineers are experimenting with other methods. One involves injecting warm water into hydrate deposits to destabilize them, a bit like coaxing steam from a sponge. Another approach, tested in China's South China Sea, used carbon dioxide to displace the methane from hydrate cages. The idea was clever: swap one gas for another, releasing energy while capturing carbon. In theory, it's two solutions in one. In practice, it's like trying to pull off a hat trick in molecular billiards. All these techniques share a core dilemma: the very act of extraction risks destabilizing the surrounding sediment. If the hydrate acts as a kind of glue, binding grains together in frozen unity, then removing it might cause collapse. Slumping sediments could not only damage equipment, but also trigger unintentional methane release into the ocean or even the atmosphere. And then there's the broader concern: are we simply adding another fossil fuel to our inventory at a time when we should be subtracting? Supporters argue that methane hydrate could serve as a transitional fuel, cleaner than coal or oil, more flexible than solar or wind. If extracted carefully, they say it might buy time for a global shift toward renewables. But critics worry that even a well-intentioned methane economy locks us into combustion pathways we can no longer afford. There's also the risk of perception. If hydrate mining becomes feasible, will nations double down on fossil fuel infrastructure instead of investing in long-term climate solutions? I once spoke with an energy analyst who likened hydrate extraction to trying to responsibly light a match in a fireworks factory. You might manage it, but the stakes are uncomfortably high, and yet the pressure to explore continues. Countries with limited domestic energy resources, Japan, South Korea, India, see hydrate extraction not just as science, but as energy security. A way to reduce imports, a hedge against volatility, a ticket to autonomy, buried in their own seabeds. Some researchers envision hybrid platforms, sites that extract methane while simultaneously injecting carbon dioxide into the same formations, sequestering emissions while harvesting energy. These are early-stage concepts, sketched more often on whiteboards than on steel, but they suggest a future where the line between energy and climate mitigation might be drawn not in sand, but in sediment. It's too early to say whether hydrate mining will scale safely or remain a scientific side quest. But one thing is clear: the frozen fire beneath us is stirring curiosity, ambition, and concern in equal measure. And in the quiet shallows between caution and curiosity, countries are beginning to test their luck. If you sail east from Shanghai, then south past Okinawa, and drop anchor somewhere over the Nankai Trough, you're floating above one of the world's most closely watched methane hydrate laboratories, not a building, but a stretch of seafloor. Japan, a nation long reliant on imported fossil fuels, has been quietly and persistently chasing a dream: the ability to extract energy from the ice that burns, not just in theory, in practice, with ships, drills, data logs, and engineers in reflective vests murmuring into headsets. And despite setbacks, it remains one of the world's boldest attempts to turn methane hydrate from a curiosity into a commodity. The effort began in earnest early in the 21st century, driven in part by the desire to reduce dependence on overseas oil and natural gas. Japan's methane hydrate reserves, particularly off the eastern and southern coasts, are considered substantial. Most lie beneath deep-sea sediment, entombed along tectonic boundaries like the Nankai Trough. Some also exist beneath permafrost in northern Japan, though these are less accessible. Enter the Japan Oil, Gas and Metals National Corporation, a name that, while sounding like the headquarters of a Marvel villain, is in fact a serious public corporation tasked with pushing the boundaries of domestic energy. In 2013, aboard a vessel called the Chikyu, Japanese scientists and engineers conducted what remains a landmark test. Using a technique known as depressurization, reducing pressure in hydrate-bearing sediment, they successfully extracted methane gas from the ocean floor. It wasn't a bonanza, but the flame burned. Cameras rolled, a new headline joined the global energy narrative: Japan ignites fire ice. Since then, Japan has launched follow-up missions, refining its technology and extending the duration of extraction. A second successful test in 2017 ran for several days. This one faced problems too: a leak, equipment wear, but it proved that the process could be repeated, adjusted, and scaled slowly. Meanwhile, South Korea has been running its own hydrate programs, focusing largely on the Uliang Basin in the East Sea. With an energy profile much like Japan's: high demand, few domestic resources, South Korea sees hydrate development as a potential linchpin in its long-term energy strategy. In 2007, Korean researchers completed an initial resource assessment, estimating billions of cubic meters of methane locked beneath the seafloor. Since then, through a combination of deep-sea drilling, coring, and geophysical surveys, the Korean Gas Hydrate R&D organization has been working to identify viable sites for test production. These efforts led to the 2015 Uliang Basin pilot production test, which yielded promising data on hydrate saturation and sediment behavior under stress. Yet for all the promise, both nations face the same sobering set of challenges. First, cost. Deep-sea drilling is not cheap, especially when done with the delicacy required for hydrate stability. Specialized rigs, environmental safeguards, data collection arrays, all add zeros to the budget. Japan's test operations have cost hundreds of millions of dollars, with relatively small yields so far. That makes investors nervous and governments cautious. Second, safety. Even when small-scale extractions go smoothly, the risk of destabilizing the sediment, triggering a slump, a release, or even a localized blowout remains. Managing this risk at a commercial scale will require technological precision bordering on artistry. Third, environmental impact. Methane that escapes before combustion is a potent greenhouse gas. If hydrate extraction leaks even a fraction of the gas into the ocean or atmosphere, it could counteract the very climate benefits that natural gas is supposed to offer over coal and oil. Both Japan and Korea have invested heavily in monitoring, but critics remain unconvinced that leakage can be eliminated entirely. Still, progress continues. Japanese research teams have begun exploring hybrid methods, using carbon dioxide injection to displace methane and stabilize the formation post-extraction. The concept, while still experimental, suggests that hydrate fields might not only produce energy, but also sequester emissions. Like planting a tree that occasionally hands you a matchbook, but politely tucks the smoke underground. South Korea, for its part, is focusing on predictive modeling, using high-resolution seismic data and laboratory simulations to anticipate how hydrate layers will respond under various production scenarios. Think of it as geological chess, with methane as the queen, ice as the bishop, and tectonic stress quietly moving the pawns. And both nations have collaborated internationally, partnering with institutions in Canada, Germany, and the United States to share data, improve drilling methods, and create common safety protocols. Because while energy competition is fierce, the seabed is unforgiving. Cooperation, it turns out, is one of the few things more powerful than methane. Whether these trials will lead to commercial-scale production remains uncertain, but what's clear is that Japan and Korea are no longer asking whether methane hydrate can be extracted. They are asking how safely, and how soon. There's something noble in that, the willingness to chase a delicate dream through layers of mud and ice, even when the outcome is uncertain. And the rest of the world is watching, some with skepticism, some with hope, and many with an eye on their own continental shelves. Because for every hydrate flame lit off the coast of Japan, there's a larger question smoldering in the deep: if we awaken this frozen fire, can we ever put it back? But not all awakenings are gentle. For all the careful drills and whispering scientific censors, methane hydrate has a theatrical side. It can burst, collapse, crack, and flood. Not often, but memorably. When disturbed in the wrong way or in the wrong place, it fights back. Not out of malice, of course. Methane hydrate is not conscious. but its nature, its chemical volatility wrapped in crystalline modesty, makes it a geohazard with dramatic flair. In 1995, a drilling operation in the Gulf of Mexico encountered a surprise. A pocket of hydrate, likely destabilized by nearby activity, suddenly released gas and water, disrupting equipment and forcing a shutdown. No injuries, thankfully. But the lesson was clear: hydrate is not merely passive. When unzipped too quickly, it responds with power. The structure of methane hydrate acts like a capstone. In many sediments, hydrate forms between grains and layers, providing mechanical support. Remove it, and that support weakens. The sediment becomes softer, more prone to collapse. And if the hydrate is saturated enough, its dissociation doesn't just remove the glue, it adds pressure. Gas bubbles expand. Fluids shift. The whole system begins to pulse with instability. A 2001 study from the Norwegian Geotechnical Institute modeled how hydrate dissociation could cause seafloor subsidence. In certain cases, depressurization led to sediment slumping and cavity formation, an underwater version of a sinkhole. And when you're operating a billion-dollar drilling rig on top of that, even small movements become seismic events in their own right. In some hydrate-bearing formations, particularly those with high concentrations and coarse-grained sediment, dissociation can occur rapidly once triggered. The phase change from solid to gas creates an explosive volume expansion. Imagine an ice cube turning into a balloon inside a locked cabinet. The cabinet, in this metaphor, is the seafloor, and it does not always hold. In one particularly sobering case, researchers examining the Krishna Godavari Basin off India's east coast found clear signs that past hydrate release had triggered shallow gas blowouts. These were not caused by human drilling, but by natural shifts in pressure or temperature. The evidence came in the form of disturbed sediment layers, fractured hydrate zones and collapsed pockmarks, a silent archive of sudden exhalations. It doesn't take a large release to cause trouble. Even small pockets of methane, when released under pressure, can rapidly rise through sediment columns, creating vertical gas conduits that destabilize overlying layers. These are sometimes called gas chimneys, not because they warm your living room, but because they carry carbon skyward with startling efficiency. In the Black Sea, sonar surveys have revealed dozens of such features, columns of gas that trace old fault lines and show signs of repeated activity. It's unclear how many are connected to hydrate destabilization versus other gas sources, but the principle remains: once the barrier is breached, the path is open. There have even been murmurs, faint, controversial and still debated, about methane hydrate contributing to past disasters. The theory goes like this: a drilling rig, unaware of underlying hydrate, drills too deep. The disturbance destabilizes the hydrate. Gas releases. Pressure builds. A blowout occurs. Some have pointed to this as a possible contributing factor in historical offshore accidents, though conclusive evidence remains elusive. The truth, as usual, is layered. But even without catastrophic incidents, the risks are tangible. In shallow Arctic waters, for instance, thawing permafrost can release methane from hydrate deposits below. If this occurs beneath infrastructure, like pipelines, docks or even research stations, it can lead to surface collapse. The landscape itself shifts, sagging like bread dough pulled too long in the sun. One study in Alaska's North Slope documented these changes in alarming detail. Satellite imagery showed entire regions where the ground had sunk by several meters over just a few years. Not all of this was due to hydrate loss. Melting ground ice played a role, but the message was clear: the Arctic is moving, and not always gently. To be fair, most hydrate extraction trials so far have been cautious, controlled and uneventful in the best way. But as interest grows and projects scale up, the margin for error shrinks. A poorly placed well, a misjudged pressure calculation, a slight warming in bottom waters, each could turn a quiet field into a seafloor fireworks display. And then there's the ripple effect. A localized blowout could trigger nearby hydrate destabilization. A slump in one sediment layer could unseal a neighboring gas pocket. Like dominoes laid in 3 dimensions, under pressure, and with occasional tectonic tugs. I once heard a hydrate specialist refer to some deep-sea basins as loaded moss traps. Not ticking bombs, those are too melodramatic, but structures that require delicacy, precision, and a lot of respect. In essence, methane hydrate is a marvel and a minefield. A frozen gift that, when mishandled, writes reminders in fissures and plumes. And as nations inch closer to commercial extraction, the need for that respect only deepens. Because beyond the chemistry and the models, there's a quieter truth: this ice remembers every touch. And it never forgets a misstep. Of all the proposals that scientists have floated, some elegant, some desperate, some both, the idea of using methane hydrate as a climate solution might be the strangest feather in this icy cap. The thought goes something like this. What if, instead of fearing these crystalline cages for their hidden gas, we could use them to trap even more? Specifically, what if we could inject carbon dioxide? Yes, that carbon dioxide, the planetary mood lifter, turned greenhouse heavyweight into hydrate formations, effectively swapping one gas for another. It sounds improbable, like trying to fix a leaky dam by painting over it with ice. And yet, chemically, there's logic. Methane hydrate forms when methane molecules become trapped in a lattice of water under low temperature and high pressure. But other gases, carbon dioxide included, can also form similar hydrates. And under the right conditions, carbon dioxide can displace methane within the existing structure, settling into the same cages and leaving the methane to float free. This concept, called guest molecule exchange, has made its way from laboratory curiosities to journal papers and pilot studies. In one of the early proof-of-concept experiments, researchers at Japan's National Institute of Advanced Industrial Science and Technology demonstrated that carbon dioxide could indeed infiltrate hydrate structures, kicking methane out without destabilizing the overall lattice. Like a polite house guest replacing another without flipping the furniture. The potential appeal is twofold: extract methane for energy and simultaneously sequester carbon dioxide to offset emissions. A tidy swap. Burn one gas, bury another. Field experiments have begun to nibble at the edges of this idea. In Alaska's North Slope, the United States Department of Energy funded a field trial where a mixture of carbon dioxide and nitrogen was injected into hydrate-bearing permafrost. The results were promising. Methane was released, and some carbon dioxide was captured in hydrate form. But challenges remained. Not all of the carbon dioxide stayed put, and the nitrogen behaved unpredictably. The system, while functional, was far messier than the pristine laboratory diagrams had implied. Elsewhere, in simulation-heavy studies, geoscientists have mapped scenarios in which carbon dioxide injection into marine hydrate reservoirs might work, especially in high-saturation, sandy sediment layers. These environments, with more porous grains and robust hydrate networks, provide more space for gas exchange and less risk of catastrophic collapse. But there are caveats. Many, in fact. First, the thermodynamics. Carbon dioxide hydrates are slightly more stable than methane hydrates, which is helpful, but the exchange process is sensitive to temperature and pressure. A small shift in either can lead to partial dissociation, sediment weakening, or incomplete capture. Second, the kinetics. In plain language, the process is slow. Gases must diffuse through tiny pore spaces and hydrate boundaries. In the time it takes to displace a respectable amount of methane with carbon dioxide, a glacier might move a few meters. Patience is a virtue, but energy markets are not known for their meditative calm. Third, the uncertainty. Much of what we know about gas behavior in hydrates comes from computer models and core-scale lab tests. The deep sea, with its quirks and creatures and continental nerves, doesn't always obey equations. There's also a profound ethical wrinkle. Do we want to inject large quantities of carbon dioxide into places we can barely monitor? Subsurface sequestration is already contentious. Add in hydrate chemistry, tectonic risk, and microbial ecology, and the questions multiply. What if the carbon dioxide doesn't stay put? What if it alters the local geochemistry, harming benthic ecosystems? What if a future earthquake undoes our careful entombment? A group of scientists at Germany's Geomar-Helmholtz Center for Ocean Research have argued that hydrate-based sequestration could be part of a larger carbon management portfolio, but only if coupled with robust long-term monitoring and international oversight. They caution against treating it as a silver bullet. More like a silver cork, one researcher told me. Useful, but you still need the bottle to hold. Some engineers imagine hydrate fields functioning like deep-sea vaults, sealed, stable, quietly holding carbon for centuries. Others worry that the vaults may occasionally rattle or leak, becoming slow-drip time bombs. There's also the matter of public trust. Geoengineering, of which hydrate sequestration is one small branch, carries the scent of hubris. We have not, historically, been the best stewards of buried things. Radioactive waste, old pesticides, plastic microfibers, we tuck them away and hope they forget the way out. Still, the idea persists, because the scale of the climate problem is such that every viable option gets a hearing. And methane hydrates, for all their danger, sit at an intriguing crossroads: energy, storage and transformation. Some researchers are now exploring hybrid scenarios, extracting methane for energy, using a portion of that energy to capture carbon dioxide from power plants, and injecting it back into the same reservoir. A kind of closed-loop climate tango, danced slowly beneath the waves. But even its champions admit, this is not tomorrow's solution. Perhaps not even the next decade's. It is a possibility. One that might one day mature into a strategy, and in the meantime, it raises deeper questions. Not just about hydrate chemistry or sediment physics, but about how we choose to intervene. About when a solution becomes an illusion. About what we're willing to bury to save the air above us. Because ice that burns is strange enough. But ice that swallows flame, now that might be the greater mystery. There's a stretch of seafloor off the southeastern coast of the United States that breathes in a slow, unsettling rhythm. Known as the Blake Ridge, it is one of the most studied marine hydrate provinces in the world, not because it is the largest, but because it is restless. Here, along the outer continental slope beneath the Atlantic, thick layers of methane-rich sediment are folded into gentle arcs by ancient geological pressure. The hydrate deposits stretch beneath the seabed like ribbons of frozen breath, sometimes several hundred meters thick. From the surface you'd never suspect the seafloor holds such tightly packed secrets. But the ridge is quietly active, and researchers are listening. Hydrate presence in Blake Ridge has been known since the 1970s, when seismic reflection profiles revealed peculiar features: layered sediment suddenly disrupted, reflectors dimming or brightening in odd ways. Later, deep-sea drilling confirmed the suspicion: thick, hydrate-saturated sediments, with gas pockets lurking just beneath the stability zone. But what makes the Blake Ridge particularly unnerving is its flirtation with instability. Buried within its slopes are signs of ancient landslides, massive movements of sediment that at some point gave way and slid into the abyss. These submarine landslides left scars visible in sonar maps: chaotic debris fields, slumped sediment waves, abrupt changes in slope angles. And what sits just above many of these scars? Hydrate deposits, perched like frost along the edge of a sagging roof. Geologists believe that some of these past landslides may have been triggered by hydrate dissociation. As ocean temperatures warmed, even slightly, the upper layers of the hydrate stability zone would have shifted downward, destabilizing the sediment above. Pressure changes, tectonic nudges, or even slow seepage of gas could have turned a quiet shelf into a collapsing slope. A study led by Carolyn Ruppel and colleagues at the United States Geological Survey modeled this phenomenon, and found that small shifts in bottom water temperature, less than 1 degree, could have significant consequences for hydrate-bearing slopes. The danger is not in sudden earthquakes, but in the slow erosion of equilibrium, and that's where we return to the breath. Methane is seeping from the Blake Ridge today, rising through faults, fractures, and small conduits like gas through a straw. In some areas, remotely operated vehicles have captured shimmering bubble plumes escaping the seafloor, forming cold seeps surrounded by microbial mats and life. In others, the gas rises invisibly, detected only by sensors and isotopic analysis. One such area, dubbed the breathless slope, contains hydrate-laden sediment layered over what researchers call a gas-charged zone, a layer of free methane gas that is too deep and too pressurized to escape easily. For now, but the concern is that warming waters may someday weaken the barrier. The hydrate may dissociate, the seal may break, and the gas could surge upward in a sudden buoyant rush. Whether that rush reaches the atmosphere is uncertain. Much would be dissolved or consumed by microbes. But in shallower parts of the slope, a release could be swift and significant. Already, studies using sonar and acoustic monitoring have detected changes in gas flow rates over time. What was once a modest seep can become a column. What was quiet can become noisy, if not in sound, then in signal. Then there are the pockmarks. Scattered across the slope are shallow, circular depressions in the seabed, some only a few meters wide, others as large as city blocks. These are thought to be the scars of past gas eruptions, where methane built up beneath the hydrate layer, breached it, and escaped in a sudden burst. The seafloor collapsed slightly, leaving behind a shallow basin. Over time, these basins fill with sediment, but the pattern remains testimony to ancient hiccups in the Earth's gaseous digestion. The Blake Ridge is not alone in this. Similar features have been found off the coasts of Norway, West Africa, and even New Zealand. But Blake Ridge's proximity to the Gulf Stream, a powerful ocean current with variable warmth, makes it particularly sensitive to climate-driven ocean changes. As the Gulf Stream shifts or pulses, it brings warmer water across the slope, nudging the stability zone downward and teasing the hydrates below. In recent years, oceanographic cruises have returned to the area again and again. They take core samples, they measure pore water chemistry, they deploy autonomous sensors and listen for the faint crackle of gas moving through sediment. It's not flashy science. There are no explosions, no movies made about hydrate plumes swallowing cities, but in the quiet persistence of the work lies its importance. Because the Blake Ridge is a living archive, a place where past releases are etched into the mud, and future ones are brewing in the margins. It reminds us that not all climate stories are written in polar ice or jungle canopy. Some are written in layers of silt, in bubbles of ancient breath, in slopes that lean just a bit too far forward. I once asked a marine geophysicist what it was like to study these underwater slopes. He shrugged, then said, "It's like listening to a mountain try not to sigh. And in that sigh, if it comes, there is more than gas. There is history, energy, memory, and maybe, just maybe, a chance to learn before the next exhale begins." Some engineers dream of machines that will save us, but the ocean has had its own caretakers all along, tiny, tireless, and quietly extraordinary. They live beneath the surface, far below the reach of light, tucked into sediments that smell faintly of eggs and eternity. They do not possess eyes or ambitions, and yet these deep-sea microbes shape the fate of methane on Earth more profoundly than any technology we've yet invented. At the heart of their strange chemistry is a process called anaerobic oxidation of methane. In simpler terms, they eat methane without using oxygen. Instead, they use sulfate, another molecule abundant in seawater, as an electron acceptor. The result is a reaction that transforms methane into carbon dioxide and water, all within the slimy confines of microbial colonies. It sounds modest, but in hydrate-rich regions this process prevents vast amounts of methane from ever reaching the ocean, let alone the atmosphere. Think of these microbes as filters, living sieves buried in mud, intercepting gas as it tries to rise. The key players are two very different organisms working in concert. On one side, anaerobic methane oxidizing archaea, ancient microorganisms that thrive where others falter. On the other, sulfate-reducing bacteria, often forming tight-knit consortia with their archaeal partners. They are microbial odd couples, exchanging molecular gifts in symbiotic cooperation. Researchers like Victoria Orphan at the California Institute of Technology have spent years studying these consortia. Using techniques such as fluorescence microscopy and stable isotope tracing, her team has been able to watch these microbes in action, slowly but deliberately, turning methane into something less dangerous. They colonize cold seeps, hydrate mounds, mud volcanoes, anywhere methane bubbles up from below. In the Gulf of Mexico, thick microbial mats spread across hydrate outcrops, their pastel colors hinting at the biochemical exchanges beneath. In the Haakon Mosby mud volcano, off the coast of Norway, microbial communities form dense carpets, constantly modulating the release of methane through metabolically orchestrated restraint. It's not just the gas. These microbes also influence the structure of the seafloor. By changing local geochemistry, they help precipitate carbonates, minerals that harden the sediment and create small reef-like features. These structures, in turn, provide habitat for other deep-sea organisms, clams, tube worms, even fish. Entire ecosystems form around what is essentially microbial breath. And then there's the sediment stability. Some scientists believe that microbial activity can reinforce hydrate-bearing sediments by reducing free gas buildup. That is, by consuming methane before it accumulates dangerously, they may help prevent pressure-driven eruptions or slope failures. They are not just consumers of gas, they may be structural engineers in their own microscopic way. Still, their power has limits. In places where methane flow is too rapid, such as during sudden hydrate dissociation or tectonic disruption, the microbial filters are overwhelmed. The gas rushes upward, bypassing their metabolic checkpoints. In these cases, plumes reach the ocean, and depending on depth, may even enter the atmosphere. This bottleneck effect is being studied at sites like the Svalbard margin, where methane seeps have increased in activity over recent decades. Microbial communities there show signs of adapting, but not always quickly enough. The carbon budget of the ocean may ultimately depend on how fast these microbial custodians can evolve or respond. There's also the question of warming. As ocean temperatures rise, metabolic rates in deep-sea microbes may increase, but so too does the likelihood of hydrate destabilization, which could overwhelm their capacity. It's an arms race of temperature and time. Despite their size, or perhaps because of it, these organisms remain challenging to study. Many cannot be cultured in labs. Their metabolic pathways are still being decoded. New techniques, such as metagenomics and sediment microprofiling, are revealing astonishing diversity, suggesting that we've barely begun to map the full community. I once heard a microbial ecologist describe them as the librarians of the deep. They catalog methane, not with index cards, but with enzymes, carefully shelving it back into the sediment, out of circulation. And like any good librarian, they ask little in return. A bit of sulfate, a bit of silence, maybe a steady temperature. Their work is not showy. There are no flashing lights or celebratory headlines, but without them the Earth would likely be warmer. The oceans more turbulent, the balance more precarious. So when we talk about the potential of methane hydrate, the fire it contains, the heat it threatens, we should also speak of the quiet forces that keep it in check. Not with drills or algorithms, but with cooperation, patience and microbial grace. Because long before we thought to manage methane, these tiny beings were already doing it, tending their seeps, filtering the breath of the deep, and stabilizing a world they cannot see but fundamentally shape. High in the northern latitudes, where the ground stays hard for centuries and summers arrive like a rumor, change is unfolding with unnerving speed. What once thawed gently now melts in earnest, and beneath that thinning crust of frost and time, methane waits. The Arctic, once a realm of near permanence, its permafrost sturdy, its seafloor steady, is becoming less so by the season. And with each fraction of a degree in global temperature rise, the frozen layers that hold methane hydrates grow a little more fragile, a little less still. Permafrost, that icy glue of ancient soils and moss-locked memories, is no longer the reliable vault it once was. In Siberia, vast swaths of tundra have begun to sag and slump, creating thermokarst landscapes that resemble lunar topographies. Hills collapse into bubbling ponds. Entire stretches of ground crumple, leaving behind scars and stories, and the occasional startled reindeer. In the Yamal Peninsula, satellite imagery has revealed dozens of craters, some small, others big enough to swallow a house, believed to result from methane explosions. Researchers speculate that warming temperatures allowed hydrates within the permafrost to destabilize, build up pressure, and then release explosively once the overburden could no longer contain the gas. The result is dramatic, Earth literally torn from within, revealing smooth-walled voids where frozen ground once quietly held its breath. Offshore, in the Arctic's shallow seas, similar stories are emerging. The East Siberian Arctic shelf, once a dark, cold frontier, is now a focus of intensive study. Here the seafloor is relatively shallow, allowing any methane released from the sediments a direct path to the atmosphere. Natalia Shakova and Igor Semiletov, scientists who have studied this region for over a decade, have documented increasing methane flux, particularly during warmer summer months when sea ice retreats and water temperatures rise. Their surveys, some conducted via aircraft, others from ships, have captured methane plumes up to 1 kilometer wide. In some places, the gas seems to escape in pulses, like sighs. In others, it rises more continuously. The team's findings sparked both excitement and anxiety in the scientific community. Excitement because such releases had been theorized but rarely observed. Anxiety because of what they might portend. and still there's debate. Some researchers caution that while these methane seeps are real, they may not be new. Rather, they argue, improved instrumentation and more focused surveys are simply revealing processes that have been going on for millennia. Methane, they say, has always trickled from the seabed. What's changed is our ability to notice. Yet the counterpoint is compelling. Temperatures in the Arctic are rising faster than almost anywhere else on the planet, and that heat is not stopping at the surface. It seeps downward, thawing sediments, warming permafrost, and gently coaxing hydrate fields toward instability. One particularly vivid study, published by marine geologist Guilherme Camargo, modeled the impact of projected Arctic warming on hydrate stability. The results suggested that up to 70% of shallow water hydrates in the Barents Sea could begin dissociating within a century if current trends continue. That's not a collapse tomorrow, but it is a lean toward a future with more gas in motion, and where gas moves, the landscape follows. Across northern Canada, Scandinavia, and Alaska, roads are warping, pipelines are bending, and buildings are listing as the permafrost beneath them thaws unevenly. Engineers are scrambling to retrofit foundations, monitor ground temperature, and adjust designs to account for soils that used to be frozen solid and are now quietly turning to pudding. In one community in the Northwest Territories, a school had to be evacuated after its floor cracked. The culprit, subsurface ice, had melted, destabilizing the building's foundation. The school was only a decade old. These are not just inconveniences, they are harbingers. When the ground itself becomes unreliable, everything built upon it, whether structures, expectations, or climate models, must adapt. And yet, amid this slow, sodden upheaval, science presses forward. Hydrate monitoring stations are now being installed in key Arctic locations. Seafloor observatories, equipped with gas flux sensors and temperature probes, are collecting data year-round. Researchers are developing satellite algorithms to detect subtle shifts in ground elevation, early signs that the permafrost may be breathing deeper than before. There are even discussions of emergency interventions, artificial cooling systems, snow insulation blankets, and subsurface barriers designed to slow thaw. These are early-stage ideas, some verging on the experimental, but they reflect the urgency. Because while the deep ocean holds vast hydrate reserves, it is the Arctic, shallow, vulnerable, warming fast, that may serve as the world's first large-scale test case. Here fire and ice no longer live in metaphor. They meet beneath thawing moss and rising tides, speaking in muffled burps and silent landslides. The flame is ancient, the melt is new, and in that uneasy meeting lies a question: how much breath can the earth release before it alters the rhythm of our own? It is a peculiar twist of nature that the very substance that could hasten climate disruption, methane trapped in ice, might also hold a fragment of the answer. Not a solution in itself, perhaps, but a paradox worth holding, that the flame beneath the waves, if approached with humility and restraint, might help steady the world it threatens. This idea that methane hydrates could offer both danger and deliverance has captivated scientists and policymakers alike, not because it is easy, far from it, but because it forces us to reckon with complexity, to imagine a world where risk and promise come folded together in the same shimmering lattice. Energy demand continues to grow. Even as renewable sources expand their reach, much of the world still relies on fossil fuels to power its cities, heat its homes, and cook its meals. In this context, methane, especially when burned efficiently, offers a cleaner alternative to coal and oil, and hydrate, if extracted carefully, could supply that gas in abundance. The key word, though, is carefully. Any vision of methane hydrate as a stabilizing force hinges on an extraordinary level of precision. Extraction methods must minimize leakage, monitoring systems must be continuous and comprehensive, microbial ecosystems must be protected, and hydrate fields must be chosen not merely for yield, but for geological safety and long-term sustainability. Some researchers have proposed integrated systems, methane extraction paired with carbon dioxide sequestration, real-time environmental monitoring, and adaptive engineering platforms. These platforms would not just take, but also give, re-injecting captured carbon dioxide into the same formations, maintaining structural integrity while offsetting emissions. In an ideal scenario, such systems could act like lungs, exhaling methane for energy, inhaling carbon dioxide for storage, and breathing in harmony with the rhythms of the planet. It's an elegant image. Whether it can be built is still an open question. Japan and South Korea, as we've seen, are leading the way in this field. But other nations are quietly joining the conversation. India is mapping hydrate reserves in the Krishna-Godavari basin. China has reported early production successes in the South China Sea. The United States, through the Department of Energy, continues to fund hydrate research in Alaska and the Gulf of Mexico. At international forums, hydrate is no longer just a footnote. It's a topic of cautious excitement, an emerging frontier where science, policy, and environmental stewardship must converge. Still, many scientists remain skeptical. The risks of destabilizing marine sediments, releasing greenhouse gases, or harming fragile deep-sea ecosystems are very real. Hydrate extraction is not just a technological challenge, it's a moral one. To proceed means balancing the urgency of energy needs against the long arc of planetary health. I once attended a small conference where a geochemist closed her presentation with a slide that read, "Just because we can, doesn't mean we should. But if we must, we better be kind." That sentiment lingers, because methane hydrates are not villains. They are the quiet result of life and pressure and time, accumulated breath stored in crystalline sleep. Their destabilization is not their fault. It is the outcome of broader planetary shifts, many of which we have set in motion. And yet, in studying them, in trying to understand their patterns and limits, we may learn how to move more gently across the Earth's deeper layers. We may learn how to listen, not just to what we can extract, but to what we must protect. There is something deeply poetic in the notion that Earth stores both peril and possibility in the same form. That fire can lie dormant in ice, that a bubble might carry the weight of a climate, or the whisper of a solution. So as the world looks toward new energies, new equilibria, and new ways to inhabit this spinning rock of water and memory, let us not forget the strangeness and wisdom of methane hydrate. Not just because it burns, but because if handled wisely, it just might help us cool the fire. Thank you for being here. If you enjoyed this little journey into the secret life of fire, ice, and everything in between, please consider leaving a like, subscribing, or leaving a comment. Sleep well, fellow traveler. The trees, the stars, or the atoms are whispering, and you're always welcome here.